All right. All right. So I want to thank everybody for being here. I'm going to do the best I can. The internet keeps cutting out where I am. So I'm randomly, well, not randomly, I'm making certain of you co-hosts so that if I disappear, hopefully things will continue. I wanted to introduce you to Dr. Delores Knipp. I should have checked with you with the pronunciation of your last name. Am I on track so far?
I go either way. I use the German pronunciation with the hard K most of the time, but I'll answer to either.
Okay. Well, I will go ahead and say Knipp then, because I've got a German last name as well. And I get a lot of people saying Weeble, but it's Weibel, or it should be Weibel. But anyway, going back to you. Dr. Knipp earned her PhD in atmospheric science from the University of California, Los Angeles. So Southern California, represent, very good. Currently, she's in Colorado as a research professor in the SMED Aerospace Engineering Sciences Department. She's also a senior research associate at the National Center for Atmospheric Research, High Altitude Observatory, didn't mean to leave the last few words off, and an associate of the University of Colorado Space Weather Technology Research and Education Center. So there's a lot of acronyms in your life, I can see.
Yeah.
She does really fascinating work on space weather, which is something that a lot of people don't know exists. And she's here to kind of mark the 50th anniversary of a really terrific and impactful solar storm that was going on about 50 years ago this week.
Right.
So I will turn over to you, Dr. Knipp. Thank you very much.
All right, I'm going to share screen here, see if that works. And I think I've got it. And we'll do one more little effort here. All right.
There we go.
Looks like I'm on. So greetings, everyone. I think most of you are in Michigan, as I understand it, Central Michigan, but I think we have a few folks from kind of my neck of the woods, and maybe from even Missouri and Maine online. So I'll say greetings to you. And as Deanna said, space weather is something that, yes, it does exist. I did not know that until I joined the Air Force as a aviation weather forecaster, and spent about 4 years doing that. And then I was sent out to Colorado Springs to support the North American Aerospace Defense Command, NORAD. And suddenly I had to learn a little bit, or even a lot, about space weather in short order. That happened in 1982, about 1980, about 10 years after this event. But I didn't become aware of this event until very recently. I had the good fortune to work with people kind of all over the world. And I'd written some other stories about space weather gone bad. And I got a phone call from, not a phone call, an email from a friend of mine in Australia, and said, "Have you heard anything about this event in 1972? And I had not, but the rest is history. So I will proceed to tell you about that. So we're going to look back 50 years to an event that originated at the sun and essentially really rattled our geomagnetic protective cage. So I love this diagram. This was actually created by the Australian Broadcast Corporation after Brian Fraser, who was my contact in Australia, brought this story to light. And the reason I like it is it's something that I could actually draw. I'm not much of an artist, but I was reasonably good with crayons. So what I want to point out is, A, it's not to scale, but it contains everything that we're going to talk about. It contains a sun with some sunspots and something that looks like it might be sending out material from the sun. And it's got some wiggly lines here. Those are, I think, representative of the sun's magnetic field, which is always being shed and sent out into the interplanetary medium at supersonic speeds. And after an appropriate transition period, which is typically about 3 days, it'll arrive at our doorstep. Now, it does not actually, in general, touch the Earth because we are blessed to have this marvelous magnetic umbrella around us that essentially holds off most of what the sun has to offer in the space weather realm, but not all of it. And when the sun gets really feisty, well, our magnetic field has a tougher time holding it off than when things are quiet. And when it does need to hold off an onslaught of the solar wind, what it will do is change the shape of its magnetic field lines, and changing those magnetic field line shapes generates current that can actually flow all the way down pretty close to the surface. And that is what this story is about. So here's a prettier diagram up in the right-hand corner, drawn by NASA. So they obviously didn't use crayons. They got a little bit nicer hand, but it gives you the same picture. Now, rather than showing the sunspots, here's the solar flare. Here's some of that solar wind with its embedded magnetic field still coming at Earth, and it's still not to scale, but that's okay. The one thing that it does point out is that as the solar wind gets to interact with our magnetic field, when things get a little interesting, it actually will create very beautiful aurora. And that's what those little green circles are up there. So here's my storyline. Now that I've explained that again, we're going to talk about space weather and the fact that it exists and where its roots are. And then we'll talk about space weather in the modern era. The modern era usually is what I consider to be the space age, but even finer than that, about the time that we were actually putting spacecraft on orbit so that we could look at the sun from above the Earth's atmosphere, which actually blocks a lot of the solar signal. That's when the modern era is for me, and that was in the late 60s and early 70s. So I have another item here that says what could possibly, and it should be a Y and not an E, go wrong. Well, I've done a number of these stories, but we're going to look at what could possibly go wrong and what did go wrong in August of 1972. And I'll tell you the story, and then we can have some time for questions and discussions. So the sun is actually pretty rhythmic, and Galileo started looking at the sun and sunspots way back in the 1600s. And even though the sun went quiet after his discovery, and there were others who were making those discoveries at about the same time, once people really started using their telescopes, they could count the number of sunspots. And you can see this oscillation here, and this oscillation seems pretty regular. It's about every 11 years. And at the peak, we call that solar max. There's a maximum number of sunspots. And down here at the bottom, sometimes, often, for several years, the sunspots will go to zero. And that's kind of our marker of the rhythm of the sun. It's in every 11 years. And I'm going to just bring you right over here to tell you that we are starting our 25th 11-year cycle, counting these spots. And there's been quite a bit of controversy about whether or not it's going to be a really active cycle, which tend to be marked by these very rapid rises. And this purple line here indicates that the solar activity is rising more rapidly than we had anticipated. So for those of us who are funded to do space weather research, we're kind of really hoping that this will happen. And those who operate spacecraft and power grids and what have you are kind of hoping that it won't. We shall see. So here's the background. Here's our sun again. And I'll point out now that we live within the atmosphere of our magnetically active solar neighbor, the sun. The sun is always shedding its magnetized atmosphere out into space as a solar wind. If you were to go out in space, you really couldn't feel it. It's so very tenuous. But our magnetic covering definitely feels it. The speed is supersonic, but it's not very steady. It's always coming out of these regions that you see kind of dancing around here, and the sun is rotating as this happens. So it sends out these bursts of dense magnetized plasma as the sun kind of spins on its axis every 27 days. More of them, called coronal mass ejections, appear when there are a lot of sunspot maxes. And when we get a lot of them coming out together, many of them come out fast, some of them come out slow, and that means that they can form a train or almost a train wreck where some are piling on top of each other. And that's going to be a key part of the story that I tell you. No matter what, Earth is always sampling some of these flows. And we have, in the last decade or so, been amazingly fortunate to start actually taking pictures of the solar wind. And so I thought I would show you this from about 10 years ago. And now we're actually doing what we call heliospheric imaging, and you get to see these gusts in the solar wind. This was just fascinating to the scientists who are, studying this kind of thing. All right. So let's move on to the roots of space weather. We have been looking at the sun from above the Earth's atmosphere for well over 50 years now, or at least trying to. Recently, we launched a spacecraft called Solar Dynamics Observatory. It's been in orbit over 10 years. And what the scientists have done for this particular image is they've gone back and looked at the snapshots, and every time that there was a significant sunspot or active region, they took a picture and then they superimposed them. Now, your eyes would never see this because this imagery is being made in X-rays, and you have to get above the Earth's atmosphere to get out of the way of the blocking so you can actually see these X-rays. But to me, this is a whole solar cycle's worth of active regions all condensed down into one picture. And it kind of provides this daily, this is a consolidated image, but a daily visual of these intense regions of magnetized activity that ebb and flow over 11 years. They tend to start at the beginning of a solar cycle at mid-latitudes on the sun, and then they progress down to lower latitudes, then they disappear, and the whole process starts over again. That process starts over again because of something called differential rotation. That means that the sun's middle section is moving faster than its polar sections, and so it wants to stretch out these magnetic fields and then end up knotting them up, and that these knots essentially create these very bright regions of X-rays and extreme ultraviolet light. Okay, so one more on what is space weather. So space weather is actually the events and disturbances in that flow that originate at the sun. They'll propagate and interact with geospace, with geo meaning Earth space, and produce impacts on humans and signals and engineered systems. Certainly in the case of the 1972 event, it hit the signals and engineered systems pretty hard. Luckily, we did not have humans on the moon or on the way to the moon. This happened between space shots because we think the result of this would have been very, very hard on the astronauts' health. Don't know if they would have died. There are some people who think that could have been a possibility, but they probably would not have been very happy campers in their transit to and from the moon. But that didn't happen, so we're fortunate with that. What I have up here in the right-hand image is a picture from this morning, white light image. Folks have been taking pictures of the sun since they found out that there were sunspots. And I would have typically shown you one of the X-ray images, but someone managed to, let's say, cut the line between the place in White Sands, New Mexico, where the imagery is being downloaded, and the Stanford system in California, where it's being processed. And I think there's somebody working really hard on trying to reestablish that connection. but we just get to see what we could normally see right here with our eyes if we look through an appropriate filtered telescope. So I'm not suggesting that you go out and actually look at the sun, but that if you do, you use a really good filter. If you've done that, you would have seen early this morning a couple of regions where there are some of these knots of magnetism, these sunspots. Now, these sunspots and all the things that go with them will affect to some degree the Earth's atmosphere, perhaps creating aurora, which I happen to think are beautiful, but in times before we understood them, they were generally viewed as frightening or bad omens, or maybe sometimes awe-inspiring. More recently, since we've developed conducting technology and telegraphs, telephones, railroads, they've been viewed as not very friendly. Certainly when we're trying to communicate and navigate, especially in space, they're also considered pretty unfriendly. So humans and hardware in space and even on other planets can be impacted by these renegade sunspots if they go bad. And I just want to point out that we are in the rising phase of the solar cycle. So here's a blow up of this region that was over on the top right. And now I'm pointing out that there are 3 regions from a more recent photograph that have just popped through. So the sun is really becoming pretty active and taking a really up close and personal look. This is courtesy of Pepe Mantica, who put this on spaceweather.com this morning. So in green is this region, much higher viewing resolution. This purple one is down here. And this one over here is really interesting to me. It is a sunspot that looks quite a bit like the one that developed in 1972. It's very large and has a very deep region of cooler material, which indicates that the magnetic fields are so strong that they're actually suppressing the bubbling that usually goes on in the solar atmosphere. So this one's going to be one to watch for the next few days. Okay, so that's an active region that I'll be making note of. These sunspots underlie regions in the sun's atmosphere that have these concentrations of magnetism. And those concentrations of magnetism tend to produce 3 primary types of eruptions. Solar flares you've probably heard of. They're bursts of radiation across a really large segment of the electromagnetic spectrum. Really, really big flares can create even enhanced energy coming out that the human's eyes could see. That's generally rare. But in 1972, it happened 3 times out of 4 flares. So we knew it was really active. The impacts from solar flares, because the photons travel at the speed of light, will be within a few minutes and can last up to hours. The sun can also, in about 10% of these events, send out energized particles. These are blasts of really energetic particles and ions that can actually burrow their way into the spacecraft and into Earth's atmosphere. They can arrive in 20 minutes to a few hours and may last for days and hours. And if they do penetrate Earth's atmosphere at typically the poles, so these regions right up here in green, that means that they're going to come down and actually ionize the atmosphere and change the radio propagation characteristics to the point that you may not be able to propagate radio waves through the polar atmosphere. And interestingly, if you cannot do that, then FAA says you cannot fly through the polar atmosphere because you have to be able to maintain radio contact. So when these events occur, it's a bad deal for airlines and for passengers. And then the third item is something called ejections of mass and magnetized plasma from the sun. And these usually have 1 to 4 day travel times, with the effects lasting 1 to 2 days. And we now monitor for these blobs of plasma coming at us upstream from Earth. And we usually see a travel time of about an hour, but sometimes when they're moving really fast, it's much shorter than that. And here's just a nice video that shows you what can happen. Mercifully, this one was off to the west limb, or east limb of the sun, rather. So it gave us the light show, but not the particles and mass. So we've just kind of gone over all of this really fast. Let me just reiterate one more time what can happen when these eruptions occur. These charged particles move out into the solar wind at the time frames I've just mentioned, and they can project into Earth's upper atmosphere and the ionized part of Earth's upper atmosphere called the ionosphere during storms. And those particles can get in through these field lines that are most open because of Earth's dipole configuration, more often at the poles than not. And they are the particles that, amongst other things, will create the beautiful aurora, but will also ionize the atmosphere to where you may not be able to propagate radio waves. It can also change a chemical structure in the Earth's upper atmosphere and create polar ozone holes, which did happen in this event. Very rare. There's also the added complication that when these solar mass ejections hit Earth's magnetic field, they'll deform the magnetic field and add the complication of currents that thread through this region and actually cause heating, because when you run a current through a conducting medium, just like the old days when we actually ironed our clothes, you heat things up. And so the upper atmosphere can heat up and expand up. And that's one of our big expand outward. That's one of our big concerns right now with all of the spacecraft that are now being put into low Earth orbit, is there can be significant disruption of the well-behaved low Earth environment. And we saw that a few months ago. Some of you may know that Space X had some trouble with their Starlink spacecraft, not being able to get them to the orbits they achieved during what was even a minor magnetic storm. Okay, so humans get to experience space weather mostly by the aurora, if you're lucky. The most common auroral emission is green. That means the particles are interacting with the oxygen in Earth's upper atmosphere. If you get to see red, that means that also interaction with Earth's atmosphere, but much higher up. So it tends to be more energetic. And then for a really particularly bad storm like this one in February of 1958, we get to see really ominous blood red aurora at low latitudes. And I spend a lot of time explaining to people what it is I do. And sometimes I'm doing that with my 95-year-old dad. And I told him one time, because he was asking, what do you do? And I said, well, I studied the aurora. And he just announced, well, I've seen the aurora once. And I thought, well, that's unusual because we live in central Missouri. And I asked him to tell me about it. And he said, it was the most awful aurora. And I said, Dad, it was blood. He told me it was blood red. And he said, Dad, how old were you? And he said, it was 11. It was the 1938 storm that created two of these events within 3 nights. And so I've been able to go back and kind of connect with him because of that particular story. Okay, modern active regions. Let's look at the one in late October 2003. And then I promise I'll get to the 1972 event. So here's the sun with a bunch of sunspots that some of them are going to announce their bad behavior. And here's the flare that happened on October 28th. There were several of these. These large events are large structures, or at least 10 times the diameter of Earth. They produced severe energetic particles right after the flare. This is supposed to be a beautiful, just kind of dark background with some individual stars. but all of the stars have been obliterated by these solar energetic particles that are interacting with the telescope that's supposed to be seeing what's going on. And eventually it got blinded for a little while. But before it got blinded, we could tell that there was a mass ejection, and it appeared to be affecting the entire Earth-facing side of the storm. And it got here really fast, I believe within 23 hours, and produced really extreme magnetic disruptions, but not quite as extreme as the ones I'm going to tell you about. When we do see these events, like the October 2003 event, they produce aurora way down at low latitudes. The event in 1859, which is the Carrington event, produced red aurora visible in Panama. It's interesting, we tend to rate these events 1 through 5, and generally 5 is, well, if you're seeing aurora in Missouri, that's sort of the top of the stack of badly behaved events, but there are some that go much, much worse than that. And I spend a lot of time working with my graduate students to try and understand those. But let's just kind of say that in general, we would be thinking a bad storm is one that produces aurora down at, say, central Missouri, well south of Michigan. And also that would be a storm where you might see aurora at, say, the southern boundaries of Great Britain, which in this case, 1972, we did. So now let's try and travel back to early August 1972. Solar observers at what was the predecessor to the Space Weather Prediction Center, and indeed at observatories all over the world, had been watching an active region kind of off and on since July of 72. And the reason I say off and on is because this rotates, these regions rotate around every 27 days. So for a while, they'll appear on the backside, which of course we couldn't see at that time. But all of the observers who had seen that region recognized it as being oddly behaved. The magnetic poles within this really tight configuration were backward, which had been known since the 60s and probably even before that to be an indicator that this was really a knotted up active region. And it certainly lived up to its region. When you see a compact region like this with incredible knots that are where the poles are, the magnetic active regions are essentially interacting with each other, and they're all mixed in here together, that's a sure sign something's going to flare. And the biggest flares in almost all of the solar cycles are produced from active regions that have these general characteristics. So on the morning of on August 4th, 1972, flare it did. So here's just the H alpha. So this would have been in visible light, red light, but shown here in black and white. And so here we see it. The flare has just gone off. So I think this is about 6 UT. So about sunrise, maybe a little bit after that in Israel. So the US and its space weather monitoring system would have been on the night side while this was going on. But word spread pretty fast that things were going crazy. So the region had been given a designation before we give these numbers. This was 11/9/76, and it was a prolific producer of solar flares. And here before things got crazy was an attempt by the sun to try and keep the preceding poles separate from the following poles. And it would do that with what's called a polarity inversion line, meaning, all the poles on this side are one and the poles on the other side are the opposite. But also in this region, there tends to be really dense buildups of plasma that if the sun does decide to flare, it can hurl off into space. And what was estimated when this flare happened, and I'll go back and mention these in a minute, but this one in particular, was that the sun managed to throw off one of these filaments or prominent filaments that was about 0.6 of a solar radius in length and shed about 22% of the magnetic field that was within this region. It was really, really impressive. The sun rarely has enough energy concentrated to do that. But we knew for a while that the sun was coming up. On the 31st of July, this active region appeared just on the west limb of the sun, like the active region I just showed you from today. And once it really made its full presence known, it just went on and on, producing solar photons that ionized Earth's upper atmosphere and made dayside radio communication really dodgy. And every time it peaks up like this, these are orders of magnitude increase in energy. Essentially, dayside radio communication is absolutely impossible. And when I was telling this story a few years ago, as I understood it, one of a Navy friend, well, not someone that I now know, told me that he remembered being in Vietnam, which is part of this story, because the Vietnam War was in progress, and on Navy ships where they could kind of see each other, but they could not communicate with each other. They were dead in the water as far as communication went. So I'm going to talk about this event in particular, but we're going to now size this region down to just these fewer days and talk a little bit more just about these four regions, because these four eruptions essentially stacked on top of each other to create almost a tsunami of incoming energy for our atmosphere. So finally, a little cartoon video, courtesy of NASA, that I think will play, and I'll give you it's a cartoon version, but pretty nicely done. There are the solar energetic particles coming out. The slower ones are going to hit and interact with Earth's magnetic field, peeling away Earth's protective covering on the day side and energizing particles that are going to be snapping back and then falling into the polar zones to form aurora. So I just put 3 little screen grabs out here, because I know that goes by pretty fast, but once that material from the sun reaches Earth, it's going to really shake our magnetic field, and it's going to energize particles that are just going to rain down and make the radio communication problem even worse. So here's something that's kind of a simplified version of that shows a combination of the degree to which medium energetic particles were raining down into the high latitude regions, and to the degree to which Earth's magnetic field was just really shaking and disturbed. So even though 2 of those solar flares had occurred in this time frame right here, which I'll show you in a moment, the material from the sun hadn't really fully reached Earth. So we'll look at this region down here at a level 2 as being pretty quiet. But on the morning of the 4th, just about the time that the 3rd flare is going off, the material from the first 2 flares had merged and hit Earth. There was a little quiet period. Well, it seemed quiet, it wasn't. And then chaos breaks loose. And it continues to break loose for a day and a half, then it calms down, and then it starts again. So now what I'm going to do is, and I've shown you this little diagram here, it's associated with that G scale that I showed you. But when we hit 9, we hit the rails. That's as far as we go. And of course, it can get worse, but we just currently don't have a way of saying it's getting worse. It's just worse than worse. So here are, now I've added in these flares kind of in pink orange, and here are the first 2 that I had with the little red lines that I showed you. And they're essentially sending their material forward to hit Earth. Then another super flare hits, And that one is amazing because the material that it sent arrives at Earth in the shortest time that has ever been recorded. And let me show you a little bit about that. So here's flare 1 and shock 1. It arrives pretty fast, but not alarmingly so. Here is flare 2 and shock 2. It started away from the sun at a slower speed, but arrived really quickly. So it was tailgating the first one, just kind of constantly pushing up, saying, hey, get out of my way, get out of my way. But it can't push the other one out of the way. All it can do is stack up material. And then we've cleared out the space pretty much between the sun and Earth. And here is the third flare and its shock, which arrives at 14.5 hours later. The fastest flare we'd known about before that to arrive was about 17 hours in terms of the material from the flare actually reaching, from the mass ejection actually reaching the Earth. So this shook the whole system. And then here things calm down, and then we kind of start over with this sequencing again. I'll add just a few bits of piece of information for context. Flare 1 left the sun, or the material from flare 1 left at 1,130 kilometers per second. And I'll give you a bit of context in a moment. The second one was a little slower, but it caught up with the first one because the first one was having to push through the dense solar wind. And then the third one is coming out at an unbelievable speed, 4,000 kilometers per second. And then the fourth one is back to kind of normal speeds. These all take some time to transit and push material out of the way, so they arrive mercifully a little slower than when they start. But let me give you this for context. The typical solar wind speed is 450 kilometers per second. So these are all really high. And then the typical highway speeds, when you're not quite tailgating, but close, is about 0.03 of a kilometer per second. So this material is hauling. And as a result, it piles up and energizes particles ahead of it. And the energetic particles that can start to interact with the atmosphere and with imaging systems on spacecraft, and even with just general spacecraft functioning, are all starting to really go wild. And essentially, this was a time when we had spacecraft and their solar panels losing ability to generate solar power at the rate of 5% a day. Some of those spacecraft never recovered. Their solar panels just simply gave up. All right, so now coming closer to Earth, I'm going to show you a model of Earth's magnetosphere. So this is our protective covering, and it is modeled with conditions that are actually milder than the event where this one happened. And so here's the start of it. We've got our nice magnetic field that by just the general solar wind flow is pushed in kind of like a windsock or bullet formation. 50 seconds, we allow this plug of material moving at incredible speeds to hit the Earth's protective covering. Within 2 minutes, we've got an extreme compression. And within 3 minutes, we've got all of these magnetic fields starting to oscillate like mad. And that is the crux of the problem. When these magnetic fields start to oscillate, they will generate oscillations that go all the way down to the surface of the Earth. And those oscillations can be of such a frequency that they can interfere with long conducting systems like those in power grids. And in the case of this particular event, systems that were only supposed to be able to see slow magnetic changes associated with maybe a ship going past a sea mine. But these signals were so large that they actually imitated that signal and ended up sweeping a minefield in Haiphong Harbor. So here's just a picture of what that looked like viewed from a magnetometer, a magnetic field measuring meter in Manila, which is not too far from Vietnam. And this dashed line here indicates what the variation generally looks like over the course of a few hours. It's really very tame, just a few very minor variations. But when the first plug of material arrived, we get this huge push on the system. And then it starts to kind of stretch out. We get almost an evacuation of the field line. Then it hits again. And then all of these field lines start oscillating at frequencies that are very similar to what a mine thinks should be the signal of a ship passing it. So you might know where this is going. So again, we're talking about this time frame right in here when we've gotten worse than worse in terms of the effects of all of the particles and the magnetic field coming at Earth. That extreme compression and reconfiguration of the magnetic field was seen in almost every magnetometer at Earth. Some of them saw such a perturbation that they simply went off scale. But we managed to save some records from a few of these. And these are some of the biggest variations that have ever been registered, save maybe that from the Carrington event or the event that happened in 1921. But in particular, what was happening is in the equatorial regions, we were seeing these huge magnetic perturbations that just should not have been seen. At the same time, bright mid-latitude aurora. I'm showing you this as white and black because that's the way the camera took the picture. But there was pink and white in here, and this was taken south of London, south on the southern coast of the UK, which rarely sees such a thing. And the observer commented that it was casting shadows. It was so bright. All of Central Europe was seeing this. And the particles that were coming in to create these were so strong that they essentially made the night side of Earth's ionized atmosphere, look just like the day side. And most radio communications were absolutely impossible. At the day side, there's huge waves of traveling ionospheric disturbances kind of roaming about with a period of about 2.5 hours. On the evening side of Earth, which is where the US was, there was at about 2240, which is the time that this plug of material hit Earth, a huge change in current over northern to central Canada. And that change in current generated its own rate of change of magnetic field, which power companies do not appreciate. The Manitoba Hydro Company recorded a 120 megawatt drop in its power supply, and I believe that was pretty typical of this region throughout. I have talked with power company people who said they spent all night just trying to keep the power on along the Missouri River here, which had a lot of hydro power generation, and it was pretty much out of control. From Illinois to Iowa, there was a short cable. It was one of the first long distance cables, kind of an upgraded one that was run by AT&T. It essentially, the electric field became too large and it was done. It could no longer carry any kind of signal. All of these little red dots right here indicate where there were power perturbations. Not everybody went offline, and perhaps none of them went offline, but there were a lot of power grid managers just trying to keep the power on. In 1972, August, we didn't have a lot of air conditioners, but if you could imagine the heat now with everybody running air conditioners, I'm really not sure we could have kept the power on. It was really, really would have been a challenge if this had happened today. Okay, but to the heart of the story. I'm going to go back out into the solar wind, or actually into the magnetosphere, just at the edge where it should interact with the solar wind, but not quite see the solar wind. But the magnetopause, the place that separates the solar wind from Earth's magnetic field, started to oscillate. And suddenly these downturns here indicate that the spacecraft was actually measuring the solar wind. And that's pretty worrisome for a geosynchronous spacecraft. Some geosynchronous spacecraft actually maintain their orientation by always thinking, understanding that the field at geosynchronous orbit is going to point from south to north, which is Earth's standard configuration. And then when it sees these kinds of perturbations, it just kind of automatically says, oh, I'm really out of orientation here. I should try and flip over. And yes, that does happen. And it's bad when a spacecraft decides it's going to change its orientation by 180 degrees. So there were two shocks, but I want to concentrate on this one right here. It created a magnetic perturbation of 168 nanoteslas, which is a tiny measure of magnetic field change, but it is what we have at Earth, near dawn, near the equator. And then there were these subsequent, here's this 168 nanotesla, and then these subsequent giant oscillations. My understanding of what happened after talking with many people in this region right here, Haiphong area, where we had the sea mines to prevent flow of war materials into Haiphong Harbor for further distribution in North Vietnam, was that they were set, and they had been set, thresholds had recently been set low, probably about 150 nanoteslas, because 150 nanotesla per minute perturbation would indicate that a small boat was going by if it was loaded with a lot of metallic material. And so all of these sea mines suddenly in their small little computer minds thought, oh, we've got all kinds of boats coming by carrying material of war. And that is the story. The Haiphong Harbor destructor minefield was swept by this solar magnetic storm in August of 1972. That information was finally declassified in about 1991. U.S. Navy observers who were up flying at dawn, just as patrol, reported 24 explosions in 30 seconds, and they had no idea what was going on. They were pretty sure that the enemies, whatever that was, had come up with a new weapon to completely sweep the sea mines. And, everything that we had been planning to try and get everybody to the peace table was just going up in great spouts of water. So during the first weeks of August, and I think on the 4th and 5th of August, a series of these extremely strong flares caused fluctuations in the magnetic field in and around Southeast Asia and caused the premature detonation of somewhere around 4,000 magnetically sensitive sea mines. And this is a direct quote from one of the Navy personnel who was in charge of putting all those sea mines, reconstructing and putting them back together. And here is what that looked like all along the region of North Vietnam. They had to, over the course of 2 months, which is very hard, dangerous work, putting together sea mines, not blowing them up yourself. And those all had to be reconstructed under the order of President Nixon. I'm showing you a picture right here of what a sea mine explosion looks like. When the peace treaty was finally signed, the U.S. agreed to essentially sweep all of these mines, and they would essentially decommission themselves in 6 months, but they weren't supposed to decommission themselves in 30 seconds. So this is a picture of a Navy boat hauling a essentially a long wire past this sea mine, and it was blowing up. And this was somewhere in mid-1973. So this is not actually a picture of the event itself. So I've told you a little bit about this historical and geopolitical context. We were involved in mining the Haiphong Harbor, for better, for worse. That was approved by President Nixon to slow the stem of flow of war materials. All international ships, when the Haiphong Harbor itself was mined, were told to leave within 72 hours, and then those mines would self-arm. And then other coastal regions, the ones I just showed you about, were similarly mined in subsequent days. And then within a day or less, they all blew up. At least that type of mine. So I'm coming up here on a recap. And just to tell you that this was not the whole story of everything that went horribly wrong on the 4th of August, but it is the one that I think is perhaps most surprising and least known. Energetic particles disrupted spacecraft and their imaging systems, destabilized to some degree much of the North American power grid, blew up sea mines, and caused ongoing, long-lasting radio disruptions. And the roots of this were in this reverse polarity. It's called a delta sunspot. It's very unique. That sent eruptions through interplanetary space, that cleared the path for one of the fastest eruptions to ever arrive at Earth. And in the course of that eruption, tailgating the others, it created energetic particles that penetrated deep into Earth's atmosphere and also created these extraordinary magnetic variations. And with that, I will maybe start the discussion, because people often ask, well, 1972, 50 years ago, could something like that happen again? And it depends on what that is. We very quickly figured out what was the problem with the sea mines, and that was sorted out within a matter of a couple of months. But we rely on all kinds of things that are space activities, now space commerce, that are sensitive to space weather effects of large storms like this. And in my mind, we only very slowly get rid of sensitivities. We're no longer using telegraph lines. Okay, we've gotten rid of that, but all of these other things we rely on more and more. And I think there's a large concern in the community about whether the global positioning system, which is the US, and the global navigation systems, which are generally worldwide, how hardened they are. We've done our very best for them to be hardened against these kinds of things, but there's just all kinds of little nuances in these signals where if you lose just a couple of three, it's going to be pretty problematic. You've got to have a very organized system of spacecraft, very controlled signals to make GPS and GNSS systems operate successfully. So as I mentioned, I think now I'm probably getting ready to open it up for questions and discussions. We've been experiencing space weather for a very long time, well before Galileo noticed the sunspots, but we've become more and more sensitive to that. And as a matter of national priority, that is something that we actually need to be very mindful of, along with the other aspects of things that are changing rapidly, including our climate. So I've given you a look back at weather and space weather gone bad for this particular event. I've got my Crayola picture back up, and I would be happy to take questions and see what's going on. So I'm going to stop share. And Deanna, if you want to take over, I'll let you do that. I think you're muted. Yeah,
oh, here I am. I just wanted to thank you very much. That was so engaging and just really deeply interesting. I know there are some questions out there. So I think when we talked about it, you said that if people want to just ask a question, I think it would probably work to do, I'll demonstrate the raising your hand feature, which moves you to the front of the list if you're in gallery view. And that will let us know if you have a question. I'm seeing the occasional comment in the chat, but we'll see if people, I know there's one question because somebody told me a question. Glenn, don't put your question in the chat. Say your question. A lot of people want to put it in the chat. Okay, am I supposed to read the questions? Okay.
Okay.
All right, the question from Glenn says, a lot of funding has been spent to help identify near-Earth objects that might be a threat, be threatening an impact on Earth. Are we in good shape in monitoring the sun for any significant solar flare activity that could create disruptions on Earth, or is this an area for more vigilant survey, study, and funding?
Well, of course, those of us in this business would always argue that we do, in fact, need to view the sun in many different wavelengths. What was really fascinating in about 2012, we launched some spacecraft that essentially were able to get out ahead of Earth and behind Earth in its orbit and slowly separate. And so we actually started to see a much larger swath of solar longitude, meaning that we could see sunspots that were coming and going. And ultimately, as these spacecraft moved around, we got to see the back of the sun. And there are many who now argue, and I'm one of them, is that we really do need to spend some significant effort on what's called backside monitoring, so that we can get a sense of what's coming up and get that information into models that might run and say, well, what are the what ifs? What if not too much happens? Or what if that kind of event that I just told you about is lurking back there? So yeah, I think we definitely need to be putting as much effort into looking at our nearby star as we are looking to the at the distant stars. And I don't want to take anything away from the James Webb Telescope or the Hubble or anything else, because those are awe-inspiring things that systems that draw people to science and technology, and I really applaud that. But I really do think that we need to look really closely all the time at the backside of our sun. Long answer, short question.
Good points, though. I think Jack had his hand up first, and then there's a question from Dave that I'll read after Jack's question.
Hi, sorry, so I don't have my video on. I'm driving my parents, but this was so fast. It was really, really interesting. So I'm really glad that I listened in. And my question was, solar storms like these, is there any amount of risk to human health? Is there an increased UV exposure or anything like that? And I was just curious.
Yeah, a great question. Our atmosphere does a fantastic job of filtering out almost all of those photons that increases in photons that would be associated with something like ultraviolet. There are increases in ultraviolet energy, but our atmosphere is capable of penetrating out, of essentially shielding out most of those changes. So our concerns with human health in terms of a solar flare or a solar ejection of some kind are more limited to astronauts on orbit. And there have been a few occasions where even on the International Space Station, we've seen some energetic particles get in at levels that did not directly harm those astronauts, but they were above the cosmic ray background. And so NASA takes note of that, and NASA knows, we all know that an event like this for astronauts who are outside of the Earth's protective shield, for instance, on the way to the moon, this could be a a radiation event that could really affect blood forming organs, and blood forming organs or organs that use a lot of blood. And in the most interesting and disconcerting situation is our digestive system uses a lot of blood when it's digesting food. And that's why there's radiation sickness when people are exposed to too much radiation, is their system just kind of shuts down. So the bigger concern for most humans is if you're cruising around out in space, which lots of people say, well, the heck with it, I don't care. I want to go to Mars and I'm volunteering. But there is that concern. I would say the bigger concern for human interaction is what happens if the power grid becomes unstable, like it did in March of '89, when there was another event that wasn't quite this bad, and it shut down power in Quebec for 9 hours. We just barely dodged a bullet in terms of having that power disruption come into the Northeast. So there's a lot of money and effort being spent on convincing power companies to harden the power grid, but that also largely goes along with, there's a lot of other reasons to harden the power grid as well, including, cyber attacks and just, massive storms, that kind of thing on terrestrial weather. So another long answer to your short question, but I hope it gave you some perspective.
I don't know if Jack will answer, but your answers are very, very interesting. So definitely worth hearing the whole thing. Dave in the chat doesn't have a microphone, and he sent you the question directly, but I asked him to send it to me. He says, is the electrical interference on the Earth's surface limited to the areas where the aurora is, or is it more extensive?
It is more extensive. It extends to subaraural latitudes, and that graphic that I showed you, where we had all the little red dots, some of which went down to Texas, Alabama, and Georgia. They did not see aurora in those locations, but they definitely felt the changes of the magnetic field as it was changing very quickly. So no, it's not nearly as confined as just the aurora itself. And furthermore, we do know that sometimes these signals creep all the way down to very low latitudes. And in this case, not so much the power grid, but those magnetically sensitive sea mines really did feel the effects of those rapid changes. So we can't say that we're safe in mid-latitudes by any stretch of the imagination.
Thank you. I'll sneak in and get a question. Anybody else who wants a question, either put it in the chat or raise your hand. I'm curious whether you've happened to watch the show. I'm going to ask you a science fiction-based question. For All Mankind, which is the Apple Plus show, kind of the alternative history.
Yes. My husband's been telling me about that. He has watched it, and I'm an occasional TV watcher, but he has told me about that. And I think I know where you're going with this, but
there's a couple of questions.
Yeah.
So I guess I don't want to spoil it for anybody, although one of the things, I'll spoil season 3 a little bit, sorry. There are people who are exposed to a solar flare who are kind of unprotected. One of them is out in it for quite a long time directly, and someone else is partially in a cave actually for a little while. And I was curious about the idea that perhaps getting into a cave or something like that, you mentioned Mars, on some kind of body, how helpful that would be. And then I was also curious about something that we're seeing in real life a little bit now, solar sails, and how a vehicle, a spacecraft with solar sails would be affected if there were to be, a large ejection or something like that.
So I'll go after the first question first, because I know actually a little bit more about that. There's been a really fascinating revelation in the last few days about these lava tubes that collapse on the surface of the moon, and they stay in a kind of a shadow, and they manage to keep the temperature at about 63 degrees Fahrenheit, which is actually pretty darn comfy. Not that I necessarily would be wanting to live my life in a lava tube, but the other comment was that those tubes would probably offer some degree of protection against solar storms. So your question's really timely. Now, what exists on Mars? I think there's lots of thoughts about, well, how quickly could you excavate, and could you just build some rudimentary shelters underneath just a few centimeters of material? And, those kinds of questions are being asked and hopefully answered. I don't know the direct answer to those, but, we really need to know that before we start sending people there, even the ones who just say, I don't care. Well, I think you would care, but other people would care. About the solar sails, I don't know the answer to your question. That's a really good one, and I'll have to think about it. But my sense is that we will need to have some pretty good control systems, because while they may not be so much impacted by the actual particles from the solar wind, those particles flowing past create currents and could actually cause the system to torque and perhaps not maintain the attitude that it needs to effectively be a solar sail and do what it's doing, which is collecting power. So again, that's something I should know. I work with the aerospace engineers in my department all the time. I'm a bit more of a scientist than an engineer. But yeah, I'll go ask that question. Maybe I'll email you back.
Perfect. I would love that. Another question in the chat. In 1982, author James Michener wrote Space.
Yes.
I'm sure you're familiar. I had to say it that way because it's in all caps. I'm sure you're familiar with the story as a major solar event, as a major solar event caused problems from the astronauts on the lunar surface during Apollo 18. Did the 1972 happening serve as a major inspiration for that story? And how realistic would such a scenario like that happen today?
It was the major inspiration for Michener's Space, or for that segment of Michener's Space. And NASA has put a lot of effort into forecasting these kinds of events. It is still one of NASA's highest priorities, I think, in regard to human spaceflight. But I can tell you that these events, especially these extreme solar energetic particle events, our forecasting skill is still minimal. We would have a lot of what we call false positives if we were to implement the systems as they are integrated, as they are being built today. I think forecasting solar energetic particles is still, we're a ways off from that, but we may, if we can at least see these regions, as they're cooking up on the backside of the sun, we may have a sense that say, okay, maybe we should do this and not that during a particular several day period if we're actually on the moon or in Mars. And just to follow up on that one more time, the sun has this quirky, well, it's not quirky, it's completely natural, mode of operating where the solar magnetic field that is being pulled out by the solar wind stretches out into what's called an Archimedean spiral. So it is the regions that are best connected to the locations that are just about to go around to the west limb of the sun and go on the backside. Those regions can be just almost have laser-like focus in terms of sending solar energetic particles to Earth. You think that active region is gone, it's off to the side, not a problem. And we have actually had some events that have occurred after the active region has rotated to the backside. And that is why I say forecasting solar energetic particles is still a problem. You just think it wouldn't happen, and nature has other things in mind.
Interesting. Well, I'm probably going to wrap up soon. If there's not another question, I have one more for you. And I was curious, for someone who does the kind of work you do, how helpful or interesting are total solar eclipses? And if they are interesting, where were you in 2017 and where do you plan to be in 2024?
Great questions. Yes, they do give us a view of the sun from so many different places on Earth that we and in space that we, where we can actually look at all of the data that we collect and say, okay, how good are our solar models? So I have colleagues working at Scientific Prediction Incorporated, their company out in California, and they will make forecasts starting about 3 months ahead of a solar eclipse and then modify it as they see the sun's magnetic field and configuration changing, and all the way up to 24 hours in advance. And so I'm getting these emails going, oh, this is what we think all of those lumps and bumps on the sun are going to look like in terms of the magnetic fields that are sticking out. And in 2017, I was so fortunate to be on my dad's farm, which was underneath the path of totality for about 2 minutes. And let's see, I guess that was 5 years ago. So my dad was 90, and I kept telling him, oh man, this is going to be fantastic. And we're going to have a party in the shed, which we did. And we lots of people came around. It really was quite the social event, but my dad just couldn't wrap his mind around the idea that anybody would care much. But, when we had all these people there and it finally went to totality, he was amazed. We saw it get cooler. Birds that had been flying lost their thermals. And so they just went and sat in trees for about an hour and a half because it took a while to get the thermals running again. Things went so quiet, it was eerie. And it was just amazing. And where do I plan to be in 2024? Well, at my sister's lake house in Arkansas, because she's under the path of totality.
Very, very cool. You can tell, you could probably guess that we went to Nebraska and we're in Ravenna, and it was fantastic, but we only got a minute and 35 seconds. So I'm jealous of your 2 minutes of totality. Yeah. Still figuring out 2024. So I just want to thank you once again. This has been so enlightening, no pun intended, and so stimulating, no pun intended. I think I am intending the puns. And I want to thank you so much for speaking at our little Roger of that summer event today, our little one-off. And I really appreciate it. And if people want to get in touch with you, is there a website or something where they can?
You can feel free to share the email that you've been contacting me with. That's fine.
Okay.
Yeah, that would be fine. You can also look me up with just my name at the Smead Aerospace Engineering Sciences Department, and it'll take you to that address as well. So I get all kinds of interesting questions from various people, and I do my best to answer them in a timely manner when I can. But we're coming up on what's called the Heliophysics Decadal Survey, and it is where the scientists in my discipline and others allied fields just have a free-for-all saying, okay, this is what we really need to be studying for the next 10 years. And I'm part of the committee on that, and it's going to get wild in really short order. So if you don't hear back from me right away, I may just have my nose underwater.
Familiar with how some of these work, and yeah, I totally get that. Well, thank you. I'm glad we were able to catch you before all that got underway. And this has really made this anniversary something special. So appreciate it very, very much. Thank you. Thank you, Dr. Knipp, for coming and talking with us this evening.
And, thank you for reminding me that this 50th event was coming up, because amongst all the other things that was going on, I actually had almost forgotten about it. And so as a result, yesterday, I shared a much more detailed version of this with my Space Weather Prediction Center colleagues, but they made me use the Google virtual system, and that didn't go so well. So I'm a Zoom person. I just love Zoom. Well, sometimes I don't say that, but got too many Zoom meetings. But getting ready for yesterday made me really much more able to get ready for today and kind of put it to a level that, I think communicates with the general public. And I always appreciate having that opportunity, because one of the things I want to do is be able to communicate this science to the general public.
Well, you do it very, very well. So thank you once again. And thanks to everyone who showed up, whether that's just turning on your computer screen or driving somewhere like Jack. And we will stay in touch, and this will be on our YouTube Roger That page. So I'll put that on our Facebook page. You can find us there, but also you can just go to YouTube and it's Roger That GVSU. Give me a little bit to get it kind of sorted out, and it'll appear there pretty soon.
And I'd like to say one more thing. I'd like to give a shout out to Lee Snyder. I can see that he's on. Lee was one of the very first solar forecasters employed by the U.S. Air Force. He is a predecessor to me. I was an Air Force officer, but he did one of the most amazing forecast jobs that I could imagine for an event that occurred 5 years earlier than this, in May of 1967. And if you get a chance to read that paper, there was an event that, almost triggered World War III, and Lee Snyder was kind of kept the whole world together in his own way of doing a forecast that, prevented everybody from going crazy. So I see that he's on, and I just really wanted to say to him, thanks so much for all of the support that you provided me and an encouragement to get this kind of material out.
And wow, thank you from us too for saving the world.
Yeah, indeed. We're all here because of Lee.
Thank you, Lee. All right. Thanks to everyone, and have a wonderful rest of your evening. Take care.
Thanks so much, dear.